Hello and welcome to the micro lecture on imbalanced datasets. In this micro lecture you will learn to identify and explain challenges caused by imbalanced datasets. Then you will also learn how to choose an appropriate evaluation metrics that kind of considers that the dataset is imbalanced. Then you will learn about some oversampling or undersampling techniques, and last but not least, to apply class weighting to improve model performance on imbalanced datasets. So we will start with the question, what is an imbalanced dataset and why is it a problem? And then we will learn about some specific evaluation metrics which are suitable for that. And then we will learn about over and undersampling and class weighting. So here we have some official definition, which is a dataset is said to be imbalanced when there is a significant, or in some cases extreme, disproportion among the number of examples of each class of the problem. In other words, the class imbalance occurs when the number of examples representing one class is much lower than the ones to the other classes. Hence, one or more classes may be underrepresented in the dataset. So common real-world tasks are fraud detection because, usually the most observations are like normal data points and no fraud, and you only have a few cases of actual fraud. Then you also have a disease diagnosis, so luckily there are more healthy people than ill people, and therefore usually the disease is always underrepresented. And also in something like spam filtering in emails, you receive far more normal emails than you receive spam. And here's an example of how imbalanced dataset can be. So for example, in credit card fraud detection, you might have 99.8 legitimate transactions and only 0.2 fraudulent transactions. And the problem is just if we don't consider that the dataset is imbalanced and we use evaluation metrics such as accuracy, you might already achieve quite a good accuracy if you simply state that all transactions are legitimate without even checking. Then you would achieve an accuracy of 99.8%, which is quite great, but basically your classification is just not existent, so that's not very helpful. And in general, the imbalance can be binary or multi-class. So you can have only two options, two classes, which could be fraud or no fraud, or also different classes to classify. So as I just said, imbalanced dataset can lead to a problem because the accuracy is usually very misleading. And also, if you tune your algorithm towards the accuracy, then there might be a bias towards the majority, and that kind of worsens your algorithm. And usually it's always the minority class that matters most, so you want to identify the spam emails, you want to identify the diseases or the frauds. And the decision boundaries are poorly shaped in underrepresented regions. And overfitting can occur to the kind of naive oversampling just because one class is more represented than the other. Luckily, there are quite a few evaluation metrics which you can use apart from the accuracy. One would be the precision, which is basically the proportion of instances that were labeled correctly among those with the positive labels in the test data. You could also use the recall, which is the proportion of positive instances in the test data that were labeled correctly. And the F1 score, which is the harmonic mean of precision and recall. Then you can also look at the AUC ROC curve, and that basically illustrates a trade-off between true positive and false positive rates, or the PR AUC, which is the probability of correctly classifying the positive instances while the number of false positives being minimized. So just an example here, a model with 99% accuracy but 0% recall. The minority class is functionally useless is in a medical diagnosis, or basically in any kind of context. There are also, like, evaluation metrics is only a way to evaluate it, but there are also techniques which you can use for your algorithm to just be better in recognizing underrepresented classes. So one would be oversampling the minority class, which you can do with random oversampling, which is like simply duplicating the minority samples. That's like super easy to implement, but you have a risk of overfitting, because you do not generate any new data. However, an alternative is SMOTE, which stands for Synthetic Minority Oversampling Technique. And with this technique, you also increase the numbers of the minority class, but you do that based on the nearest neighbors algorithm. So it also introduces new instances, but it reduces overfitting compared to the simple duplication, and it can create ambiguous samples near class boundaries. As opposite to oversampling the minority class, you can also undersample the majority class to create a kind of balance. And again, here you have different options to do that. One would be the random undersampling, which just like means deleting random samples of your data, which is again very fast, simple, and intuitive to understand. But you have potentially quite a great loss of information, so be careful with that. You can also do informed undersampling. So you have here the atomic links, which removes borderline samples where classes overlap. Or you can use the edited nearest neighbors, which cleans up noisy majority samples. And just as I said, be careful, especially when the majority class contains critical diversity. Apart from over or undersampling, you can also do class weighing. And that is a technique where we tell the model that some classes are more important than others by assigning them weights during the training. And then kind of the model can process that information. So usually you are giving higher weights to the minority class, and compared to the oversampling and undersampling, you do not need to modify the dataset. It's also very easy to implement, and it's less risky of overfitting than oversampling. But it helps if your dataset is imbalanced but not extremely imbalanced. I don't know, if you have like a 90 to 10 ratio but not like 99.8 versus 0.2%. And it can be unstable if you have very few minority samples, and sometimes it's difficult to choose like the optimal weights for this procedure. In this micro lecture, you learned to understand what are imbalanced datasets and what challenges they cause. Then you learned that there are different evaluation metrics apart from the accuracy, which you can use or which you basically should use for imbalanced datasets. Then you learned about oversampling the minority class or undersampling the majority class. And last but not least, you learned about class weighting to improve the model performance. Thank you very much for your attention.